I will continue with the application problem. We have discussed yesterday in the last lecture 3 problems. Today we will take up another problem where I have a beam with different moment of inertia and I have a load applied here, can be W. The cross section of the beam is I here, whereas it is 2 high here, and let us say the length of the beam is equal on both the segments. What I am interested is to obtain the natural frequency of vibration of this. Now what is the practical significance of this problem? In drilling platforms, the supporting deck shall be designed to equip for high machinery and hence sometimes the moment of inertia will be varying, it is not be constant. So I have taken a very simple example of a fixed beam of span L where the moment of inertia of the cross section is twice of the left half of the beam, whereas I have some heavy equipments or machinery located here, therefore the beam requirement is higher in cross sectional dimension compared to this. I am going to apply a load to this beam here at this point, let us say W, and I want to find out the natural frequency of vibration of this beam. So let me name this as A, B and C. So we will use the classical mechanics for finding out this. So let us say I want to find the stiffness of the member BA and BC at joint B. It is an hypothetical joint because it is a section where the moment of inertia is changing. So KBA and KBC, so it is nothing but EI by L whereas KBC is again EI by L, where this is going to be EI by L. Let me find the sum of the stiffness of these at the joint B, which will be 2 EI by L plus 4 EI by L, which is 6 EI by L. Let me find out what I call the distribution factor which I call K for segments BA and segments BC separately, BA and BC separately. The equation is simply KBC by sum of K, this is K BC by sum of K. So I have both the values here, I can substitute that, so which is 2 EI by L by 6 EI by L, which will give me 0.33, and this is going to be 4 EI by L divided by 6 EI by L, which will give me 0.67. At any junction the sum of this should be unity. So in the first step I would like to know, because the moment of inertia of the cross section are varying distinctly at a defined section, how the load will be distributed. So I am talking about the distribution factor. I would like to know this before I want to estimate my stiffness. In the second step, I want to know what will be the forces at this point which can cause unit displacement at this point, because stiffness by definition is force which is responsible to cause unit displacement. So, where you want to cause a unit displacement? I want to cause unit displacement where the force is applied. So, at this point I want unit displacement. So, what would be the force responsible to create the displacement is what I am looking at, the stiffness of this whole beam. Why I am looking at the stiffness of the whole beam? Because the mass of the whole beam is known to me. If you know the stiffness, being an idealized single degree freedom system model, I can easily find omega n, which is root of k by m. Okay. So, I am interested in knowing the stiffness here. So, I will use the classical mechanics again to use or to derive this. Why I am following the same steps? Because this is a evident method by which people know how to find stiffness. So, we will use the same technique here, but apply it on dynamics problem for a simple example here. So, I have a beam, I have a point of interest here, I displace this point by unity without creating any disturbance to any other point. So, if you do that, obviously this will invoke a moment which is 6 EI delta by L square. Delta in my case is unity, that is by definition, and I in the left half is I, whereas L in the left half is L by 2. So, I substitute that here for this, which will be 6 E I unity by L by 2 the whole square, which is 6 E I So, let me write this value as 24 EI by L square. The same will get transferred here as 24 EI by L square. Look at the second half of the beam. Now, this is displaced. So, there will be a force applied here, and this will also be equal to 6 EI delta by L square. Delta by definition is again unity, I by definition in the problem is 2I, and L by definition in the problem is L by 2 for my segment. I substitute back again here. So, 6 E 2I unity L by 2 the whole square. So, it becomes 48 EI by L square. So, I write that value here, 48 EI by L square will have the same effect here, which is also fixed, which is 48 EI by L square. After doing this, I will do a simple moment distribution to find out the stiffness. So, I will again draw the beam, fixed, point of interest fixed, so let me enter the members. This point B, so BA, BC, AB, CB, these are my members. Let me write the distribution factor. We already saw BA is 0.33 and this is 0.67. Of course, there are no factors done for the connections which has got only one member. This is only one point, so we do not need at A and C. Now, I want to know the unbalanced moments. I call them as fixed end moments. It is not finite element method, it is fixed end moments. So, there are somewhere anti-clockwise moments, somewhere clockwise moments, I have to convert that with a numerical sign. So, I will take anti-clockwise as negative. Okay, that convention can be followed. Look at the member BA, look at the piece BA, it is anti-clockwise of 24, I enter here minus 24. Of course, the multiplier of EI by L square will remain common for the entire row, I take it out, it is not required to be written inside. Similarly, for the member AB, again anti-clockwise, so minus 24. Whereas for the member BC, it is clockwise, plus 48 and plus 48. So, at the joint B, I have got unbalanced moment, which is caused because of unit displacement created at this point, where I am interested to find the stiffness for the entire beam. So, the unbalanced moment is positive, so the balance will be negative. The unbalanced moment is positive, so the balance will be negative. If this is x, the value of x is nothing but the unbalanced value, which is 48 minus 24, in my case is 24, multiplied by the distribution factor. So, in my case it is going to be 24 multiplied by 0.33. So, 7.92. So, I will remove this, I will enter 7.92 here. And similarly, if you want to know this value, which I call as y, this value will be simply again the balance, which is 24 multiplied by 0.67, which is 16.08. After I do this balance, I do a carryover. So, simply carry over this to the next joint, carry over this to the next joint with the same sign. Quality will be same, quantity will be 50%. So, minus 7.92 by 2, which is 3.96. Then in this case mine 8.04. Try to sum them up. So, let us sum this up. 24, which is minus 27.96, minus 31.92, plus 31.92, plus 39.96. Once I get this, let me get back to step number 4. So, draw the beam again here. So, at the point B, BA had minus 31.92, which means it is anticlockwise. So, I enter it here. and of course this is clockwise of the same magnitude. Since the joint is balanced, we have stopped the iteration here, otherwise it will keep on continuing. And we look at AB, it is again 27.96 anti-clockwise, and for CB it is 39.96 clockwise. Now let us look at the segment AB. I have got a couple, or I have got a total moment of 31.92 plus 27.96 which is anti-clockwise. I want to balance this by a couple. That value is nothing but 27.96 plus 31.92 divided by this span, which is L by 2. Okay, so this value is now going to be 59.88. So I will remove this. I should say it is 59.88 by L by 2, which is nothing but 119.76. I already had a multiplier EI by L square here. So I will get EI by L cube here, there is a L again here, and this value is again 119.76 EI by L cube. Similarly, let us do for the segment BC. I have got a clockwise moment of 31 plus 39. I want again balance this by an anti-clockwise couple, and if you look at this example, let us say here this value will be 39.96 plus 31.92 divided by L by 2 of EI by L square. So which amounts to 143.76 EI by L cube, 143.76 EI by L cube. It is a classical mechanics. Now let us focus the values here. Now the question comes, why do we have to focus the values here? Because it is the point where these forces are responsible for unit displacement at this point. So I am looking at the stiffness of this problem. So both of them are downward, which is acting in the same direction as that of the force applied. So I should say 119.76 plus 143.76 of EI by L cube will be equal to my so this is going to be 263.52 EI. So if I know my mass, or if I know my W by G, which is my mass, because W is known to me, I can find omega as root of, because for K I know already Young's modulus of the member, I know the cross sectional dimensions of the member, I know length of the span or span of the member, and I know W now or M now, can easily find omega in radians per second, provided M is in kg and this is in Newton per meter. You can even check the units here, EA by L cube, E Newton per mm square. So, you will automatically get Newton per millimeter, convert that into a specific unit what you want, you will get this as so many radians per second. Now, if the problem says add weight of the beam also, this m will be m plus self weight of the beam, add the beam and do it. In all these examples there is one commonness, we are measuring the stiffness assuming the mass lump and degree of freedom at a single point. Suppose if you shift it in 2 degrees of freedom, then the problem starts. In single degree it is not there, because single degree is only an idealized point where mass is concentrated. Though the beam is a continuous mass system, I am assuming the masses of the beam is concentrated here, or neglect the self weight of the beam, do the vibration analysis only for the external force acting at a specific point. Wherever it is acting, do the same argument there, get omega. It is a very simple classical application of standard structural mechanics for dynamics problem of single degree. Even in the last example where we saw for a truss problem, again unit load method is a classical example of applying it for single degree freedom system for dynamics application. So, for single degree freedom systems, existing classical theories can be easily applied to find out vibration characteristics or dynamic characteristics of the member. Okay. Now, there is a confusion starts once when you have got a member with single degree of freedom, but forces of 2 in nature. Now, here the force is only 1 in nature, I am applying the force only in the downward direction. Suppose if you have a problem where I have got degrees of freedom in a different format, but I want to condense it to an easy format. So, let us derive what we call lateral stiffness of any given member. So, we are focusing on derivation of stiffness and mass matrices, because for single degree if you understand how they are done, for 2 degrees and multi degree it will be easy for us to then work further, because we will have no confusion on arriving at the mass and stiffness matrices. We can work further, which are more complicated than getting m and k. And the real dynamic analysis problems where you have selected an offshore platform by an innovative form, the problem starts in arriving at the k and m itself, because these are non classical structures or non simplified structures. The difficulty will start once when you start working at the stiffness matrix and the mass matrix for given innovative form which you wanted to derive for importance to put it in deep waters or ultra deep waters. So, main hitch will start only at the initial stage of the problem where you have got to arrive or sometimes derive the stiffness and mass matrices. So, the examples what we see here are very simple, because they are all single degree, 2 degree, multi degree, where the defined points are already existing. We will also talk about deriving stiffness and mass matrices for new generations of offshore platforms, where how they can be derived from first principles. So, you must understand how stiffness and mass matrices are derived from first principles. This will be a base for doing this derivation in the next module for new generation platforms, where the form is innovatively derived to suit a specific requirement in water depth. So, at that point of time k and m itself will become a nightmare, you will not be able to derive them. It is because of this reason most of the people who work on dynamic analysis on, let us say, innovative form of offshore structures depend on numerical analysis using a software. So, they model the structural system in the software, let the software arrive at the k and m for the given problem, and pathetically you do not know whether it is right or wrong. You simply keep on doing the analysis and get the results, which is wrong, because a form is innovative, you have no basis to derive k and m, Therefore, you depend on numerical analysis, where you model this in a software using a finite element mesh and let the software arrive at k and m whatever value it gets, do the analysis and get the response values, which may be absurd, which may be even wrong also, because you have no clue how to derive them. Though in this course we will not teach you how to derive stiffness and mass matrix for buildings and structures, I am taking only very few examples because many of you may not know. Even if you have qualified structural engineering in BTech program where you studied these concepts in BTech in classical structural mechanics, in my experience of this 18 years I have seen that not even a single student was able to derive this, single student, Indian and foreigner, not able to derive, and they all waste their interest only on software development, where they saying they make a black box model using a software gives them k and m, they even do not know what are the values, they do the analysis, they call them as dynamic response analysis, which is absurd, which is not correct. Now let us look at one more extended derivation of this, where I have got 2 degrees of freedom, but I want to condense it in single degree of freedom. This is exactly many softwares do for simplifying the dynamic analysis. Let us see quickly for a simple example how this condensation can be done by a fundamental mechanics. We will see this, then we move forward to 2 degree freedom system problems. Any questions, any doubt here? Because the class may address some components on classical structural mechanics like moment distribution, distribution factor, unit load method. So you may think we are deviating from dynamics to classical structural mechanics or advanced structural analysis. As I said, dynamic analysis has a foreword of analysis into it. So we must know what is that analysis is, we are looking at that now. If you all know this, I can skip this coolly and get back to 2 degree of freedom, I have no problem at all, because it will remain as a dark area for you forever, because many literature do not explain this in dynamic analysis textbooks. Many literature which talks about structural analysis do not touch on dynamic perspectives. So you will have no bridging between these two, and you will totally depend on or surrender yourself to a numerical analysis done by a software. I am not commenting on any software, they are all excellent, written by intelligent people, coding has been verified, tested, etc. But above all, you should know whether the answers derived by the software are right or wrong. You should have a checking mechanism to say closely it is right or wrong. You cannot simply surrender the whole exercise to a software developer and say this is my dynamic analysis, what x and y is giving me, that is wrong. Okay. So that is why we are exposing it to you in this format. So we did a simple truss example in the last class, we did a very simple example of a beam in this class, which are all covering the whole structural classical mechanics theory which I studied already. The one which I am going to derive now may be new for many of you. Let us see what is that newness, I mean innovativeness in that, because this is again not available in standard literature, these are all available from research papers which I am going to do now. It is very simple exercise, we will do that because I want you to have a strong basis on deriving k and m, because I am going to demonstrate it for different platforms in the next module, talking from gravity platforms, articulated towers, TLPs and triceratops. I will derive the k and m here. At that time, if you have any difficulty of how these coefficients have been derived, that is the end of your class, you will never follow further, unless otherwise you get back to this class and try to understand this once again. You will stop there, your knowledge run will get frozen there. This happens to many students in the first class onwards, but still for sure it will happen from that time onwards. Then I will show only pictures and you will keep on yawning and writing, that is not dynamic analysis. Understanding is more important. You need not have to understand 100%, but you have to understand 1% on your own and say confidently, yes I have understood 1%, my job is done. That 1% is going to be definitely basics, which we are focusing in this class. So our object is very clear. I will show you advanced analysis later, the results, research papers, I will discuss all of them in this course, but to start with I do not want to take you or travel you to that end and then bring back you and say yes I have done a great work. if you know how I have done it, at least you will believe that I have done it. Secondly, you will appreciate that I have done it, because it is difficult. If you have these two in your mind, you will then motivated to do it as similar as I have done. My job is done at that research level. So some fundamentals are very important, I cannot skip them. It may look very silly that we are discussing something on mechanics on dynamics class. Many people have asked this to me when I was teaching, but I feel it is very vital for a student to understand what I am talking in the fundamentals before I extend it to my higher level of mechanics. I must teach this, therefore it is important for us to understand. Now I have another example here where there are 2 degrees of freedom, but I want to condense it. I am putting this example 5 because 4 we have already done. So I have a cantilever beam, I have got 2 degrees of freedom for this problem now. Let us say this is my degree of freedom x and this is my degree of freedom theta. I can call this instead of x as 1 and instead of theta as 2. So far we have been thinking that if you want to know the stiffness matrix of a cantilever beam, what will you do for a loading given vertical is, this is P, this is L. If I say this is my unit deflection, this deflection is classically given by PL by 3I. If I say this is unity, the force responsible for unit deflection is my stiffness, I would simply say it is 3I by LQ. You will become jittery only when I introduce theta to it. Will it change? No guess, no clue, nothing, simply you have no clue at all whether it will change or not, because as long as theta is not introduced in the problem, you have absolutely no trouble. When theta is there, you do not know how to handle it. For such problems, we have called the derivation of lateral stiffness matrix or translational stiffness matrix. Why I am putting them as matrix, there is a reason, I will tell you this. I will also tell you what is the significance of this problem practically. First let us understand this problem. I think you are getting the gravity of this question. As long as theta is not a degree of freedom indicated in the problem, your stiffness would have been simply 3A by L cube, is that right? If theta is given, how do you handle to get stiffness? Confusion, we have no idea, okay. So we are going to do that. So I have taken deliberately 2 degrees, creating a confusion, get K, and I call that K as translational stiffness matrix or lateral stiffness matrix. There is a reason for this. Look at this as a problem of a column of an offshore jacket structure. I have a column, let us say this is my jacket platform. I am idealizing it or taking the simple example as a vertical member for understanding. I have a lateral load, pick up any segmental member, assuming this boundary condition as fixed, I have a lateral load. On the other hand, because of the weight or because of inclination, there is moment also acting here. So it is a very classical example of a member like this which has got lateral load from wave and a moment because of weight or eccentricity of the load. So it is a, you cannot idealize this problem as purely a lateral load problem and get stiffness, it is not correct. So in such situation what do we do? So let us remove this. Let us say since you have got 2 degrees of freedom here, I will now get what I call as a matrix. I call this coefficient as kxx, kx theta, k theta x, k theta theta. It is very easy to remember this. I will give you a clue. This row is x row, this row, this column is an x column, this column is a theta column, this row is an x row, this row is a theta row. So, row column, row column, row column, row column, row x, column x, row theta, column x. You can read it like this. Okay, so no confusion here. Now my job is how to get this kxx, kx theta, theta x and theta theta from first principles. Then how to get ultimately the lateral stiffness matrix. We all know already that multiply by displacement will give me the force, okay. Whatever may be the displacement, it may be rotational, it may be translational. So I will extend this equation for my problem. I should say kxx, kx theta, k theta x, k theta theta of displacement x and displacement theta should give me force x and force theta. So let us multiply the second row. So k theta x of dx plus k theta theta of d theta is f theta. So I can get d theta from here, which will be k theta theta inverse of f theta minus and so on. Look at the first row, I say kxx dx plus kx theta d theta is fx. I substitute for d theta from this equation here. So substituting for d theta, so let us say kxx dx plus kx theta of k theta theta inverse f theta minus k theta x dx will be fx. So I have got two terms here, one is on dx, other is on d theta. Okay, let us separate this. So if you look at kxx minus kx theta, k theta theta inverse k theta x of dx plus k x theta k theta theta inverse of f theta should be fx. Okay. Now compare this equation with this equation. If my delta would have been only displacement degree, I will get k in that degree and force in that degree, that is a general expression. Look at this equation, if I am looking for the force in x degree and displacement in x degree, this should be a refined stiffness only in x degree. So I call this as k bar, where k bar is my lateral stiffness matrix. So, if you want to derive the stiffness matrix once again, you may not remember it. There is a very easy shortcut to remember this. I will tell you the shortcut quickly to remember this. So, I want to remember the lateral stiffness matrix of Kxx. I can write it the same equation very simple here. See, Kxx minus K x theta K theta theta inverse K theta x. It means I must get Xx back. I am getting Xx back, theta 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 Xx back. It is very easy to remember. Now the question is not answered still. I have a cantilever beam which has unit load here or any load here only in this direction. The K was very easy to remember, whereas I had a cantilever beam where I got 2 degrees of freedom. I am going to use K bar. Will I get the same as this? If I am able to bridge these two, then derivation of K bar will be helpful for me to understand or to avoid the confusion of theta onto this problem. Is it clear? That was the confusion, right? So, I am not going to derive K from the first principles here. I will derive K for this problem using K bar and see what happens to my K bar here. Now, there is a reason why I am calling this lateral stiffness matrix, because it is very easy to understand here from a general expression. Any displacement connecting the force in a direction should give me stiffness only in the direction. That is a general algorithm. It may have components of theta, that is why I am calling this as condensed stiffness matrix or translational stiffness matrix or lateral stiffness matrix. It is equivalent matrix. It has got components of theta also into it, remember that. Okay. So, when you have confusion of this order, I can resolve it to this order using this, and this equation may not be derived, can be remembering it. It is very simple. So, I will take up this problem quickly now in few minutes, find out x theta, theta theta, theta x and xx, combine them in this equation and get K bar, see what happens. Okay, that is our objective now. So, I will rub this. Any doubts here? Okay, I will put this as theta, this as x instead of 1 and 2. So, what is stiffness? Stiffness is force which can cause unit displacement. I will pick up unit displacement along x and get the force, right. So, I draw this, pick up unit displacement along x and get the force. So, this is going to be a displaced position of my beam. So, if this is delta, this will be 6 Ei delta by L square, where this is my L, this is also 6 Ei delta by L square, delta is unity. So, there is a total moment of 12. So, I get a couple which is 12 Ei by L cube, 12 Ei by L cube. This is the force which is responsible to cause unit displacement in x axis or x direction. So, I should say K11. Why 11? Force in the first degree because of displacement in the first degree. I can also call this as Kxx, which is plus 12 Ei by L cube. Why plus? The displacement and the force are on the same direction. There is one more component which is arising because of the displacement, that is the moment. There is a moment here, okay. That moment is again going to be K, moment caused because of displacement, K theta x, okay, moment caused because of displacement, right. So, this is going to be equal to this value, this is opposite to this. So, minus 6 Ei. So, again I have got to give unit rotation. So, let me draw a unit rotation. To given unit rotation, you will have to apply a moment which will be 4 ei theta by L, which will be transferred as 2 ei theta by L, theta is unity. Now, there is a moment total of 6 ei by L, there is a couple which is 6 ei by L square and 6 ei by L square. So, now this is the force in theta direction because of unit displacement given in theta direction. So, I should say this as k theta theta, which is nothing but plus 4 ei by L, and this value is a force in x direction because of unit rotation given in theta direction, but this is opposite to the force applied here. So, I should say k x theta, force in x because of displacement given in theta, which is nothing but this value is minus 6 ei by L square, minus because this force is opposite to direction of x. So, now I have got a matrix. So, this is x and this is theta, this is x and this is theta, this is kxx, kx theta, k theta x, k theta theta. Remember, stiffness matrix is always derived column wise. First I got xx and theta x, I got this. Second I got theta theta and x theta, I got this. It is always derived column wise, it is never derived row wise. Though there is a symmetry, does not make a difference, but you must understand how they are derived. It is always derived column wise. Okay. Substitute back this quickly, I will remove this here. So, minus a matrix now. So, substitute for this value, this is going to be 12 ei by L cube minus 6 ei by L square minus 6 ei by L square plus 4 ei by L. So, I want to write k bar is kxx minus kx theta, k theta theta inverse, k theta x. This is my x, my theta, x theta. So, 12 ei by L cube minus x theta minus 6 ei by L square, k theta theta inverse L by 4 ei and k theta x minus 6 ei by L square. Simplify and tell me what you get. How much? How much? Okay, it is exactly same, but I have used a different technique. Therefore, creating an additional degree of freedom should not cause embarrassment to work out k. Therefore, people use still this number as an equivalent lateral stiffness and solve the problem. I have taken theta into consideration, still I got k bar as same as k. Okay, I must understand this why it is so. I have demonstrated it because of this reason. So, introducing an additional degree should not cause panicity in working out k. In that situation, I can use equivalent stiffness, or what I call lateral stiffness matrix, and derive it back again with a simple expression like this. We stop here, we have a next class where we talk about 2 degrees of freedom. Maybe I have to finish the 2 degree and multi degree in the next class or next 2 classes. I will extend by one more class because there are many examples I would like to show you. in 2 and multi degrees before we finish off or take quiz 1. So till quiz 1 I will continue, the quiz 1 will be next Saturday, not day after tomorrow. So we will have classes for the next week complete, as well as maybe another 5 classes I will try to complete the 2 degree and multi degree all methods including Rayleigh-Ritz procedure till quiz 1. So we can start from quiz 2 session onwards the fresh application on dynamic analysis of Gaussian structures directly. Different examples we will pick up and do dynamic analysis for them. Okay.